Then next talk will be covered by Dr. Sahil, who will be talking on of phase evolution, microstructure evolution, how you can do that simulation in a high entropy Li using the computational tools like Thermokel, and which are basically based on basic metallurgical thermodynamics. So he will take that session and have online demonstration of the talk. So let me start my talk, which is going to be a powder metallurgy processing of high entropy LIS. This is one of the emerging material which has extremely good strength compared to one. Again, I want to acknowledge some of the students who had dedicated the work on high entropy LI, which is Sahil, Rahul, Subhendu, and Chandrakant. Some of their works I will be citing here. You all know, right? Materials means we have different applications, and different applications require different kind of properties. Not one single property is sufficient to meet your all requirement. Different functionality needs different types of characteristics of the material, and this difference in their characteristic requirement lead to the development variety of novel methods of processing or novel materials. So high entropy lies one of these series which comes out. You all know when you talk broad classification of the materials, which can broadly classified in three major categories. Once you know as a polymer, metals, and ceramics. Okay, when we talk about ceramics or polymers, it has own properties and defines its own application domain. When you talk about ceramics, it has a definite properties which are they are very hard, but they are not having ductility. Polymers are typically soft and they are good for low temperature application. Ceramics are good for high temperature application. However, it will not have conductivity or it will not have ductility. So it limits the application of ceramic. Polymer properties being a soft, it limits its. Similarly, when it comes to metals are ductile, these are conductive in the nature. However, when it exposed to high temperature or when it exposed to oxidative atmosphere or corrosive atmosphere, we have issues with urine. So when we talk about pure polymers based material, pure ceramic based material, pure metal based material, so it all will have a different domain and area where it can be applied independently. However, there are a variety of your requirement where you also need high temperature, you also need oxidation resistance, but you also need a ductility. So you will have a requirement of complex in the nature. So what happened? Not one single category of material is made. So you develop something called a composite. You all know what is composite. I need not to explain you. What I am trying to say is, so that complete composite is basically give you a properties which you are expecting. So you can play with the composition and reinforcement, all those things, and you get your desired properties. So this is the broad, you can call it fourth category of material. When it comes to metal, again, there are a variety of metals are available, steels, alloys, and all those things. In this series, again, there is a new class of material, not no longer new, almost a decade old now, called high entropy alloy, which has emerged here. So we will be discussing in the metal systems where a relatively new class of alloy, which we call it high entropy, has coming out here. And now these are just conventional alloys, have variety of property and variety of applications available. There is a lot of such data you will see: ductility versus strength, density versus strength. If you knowing, this is one example where you can see x-axis plots a density of the alloy. X-axis, what you can see here is the density of the alloy. Okay, y-axis you are plotting the strength. Okay, and when you plot with increasing the density, usually you will see there is a normally increase in the strength of the material, right? So typically you see a horizontal trend. However, when it comes to the performance, there is something called specific strength. What is specific strength means? Strength divided by density of the material. So this is called specific strength. So what you see that demand for high specific material is higher. So when you move this direction, we are talking about high specific. The dotted line what you have shown here is basically the high specific material. This dotted line what you see are the specific strength of the material. So demand for not only high strength material is high. Of course, you need high strength, but these days, especially for automotive application or aerospace application, you are not only looking for the strength, but you want weight of the material to be reduced. And that leads to a material called the high specification. So our actual requirement is going in this direction. We want density to be low, strength to be high, which is not very easy to achieve. So if you look at the high entropy, these are variety of materials. You can read out if required, polymer, chrome, other things. What I want to say is all the conventional materials are like this. Okay, this is the trend. The yellow portion, what you have reason here, you can see here they are having a upper portion of high stress resistance. So high entropy alloys are typically a material with high specific strength. But what it means is that having a relatively lower density and having a higher strength. So this is where its demands are increasing. So wherever you are looking for high specific strength material, this is the material or class of material which can fill the gap. There is a word used, entropy, and I don't want to bore you by using the entropy. These details of entropy will be covered by next speaker when he does the thermodynamic modeling. Here, the typical LI design consists of 5 or more element, and whenever you increase number of elements, their entropy, configuration entropy of the system actually increase. You can see the plot here. This is the number of element which you are trying to add to make a LI, and when a number of LI elements are added, their configuration entropy actually. So whatever high entropy level will talk, most of talks will be people are mostly there are lot many elements you can edit. However, most of the LIs are, you will see, find somewhere 4 to 7 to 8 elements, and you will see that their configuration entropy is very high. This is the class of material which we refer as a high entropy LI. So what is the LI means? We are having a variety of metals A, B, C, D, E. You assume that these are all metals. These all metals are mixed together and make a single Li. Okay, it will have A, B, C, D, E, Li. So this is what is our goal. There are a lot of applications you can find because they have very good hardness. They have good wear resistance, for example. Some of the high entropy are also good on oxidation resistance as well. So you can find application in variety of, I just listed a few, like turbine blades, for example. You can have a lot of heat exchanger, gas turbine nozzles, rotors, lot of other manufacturing and other application. Since it has a good, some of the high entropy has a good oxidation resistance as well as strength, it can also find application in some underwater applications, structure applications. There are a lot of desired properties, as I said. Again, not all high entropy Li exhibit this, but there are good number of high entropy Li which gives you a good strength, good toughness, good corrosion resistance, good wear resistance, high recrystallization temperature, and control or low thermal expansion coefficient. So it can use application in several purposes. If you look at the history, actually it has been developed a long back. However, for a long time, nobody has seen that what they are able. If you look at typical periodic table, these are the metal group which basically mix together and form the LIs. Okay, and it has started all the way from 1981, but after that nobody pay attention to this element. However, 2004 actually breakthrough comes, and actual research in high entropy starts from group of called Brand Cantor, and which is in UK, where is another group, Professor Ye from Taiwan. In 2004, they published a paper independently, and from there, actually, the major attention across the globe comes from 2004 onwards. So material is almost now close to 16 years old, is a teenage. So there are a lot of scope when materials are in teenage. So huge scopes for all the people, whoever is interested. If you look at the typical characteristics, there are 4 core effect has been defined for this material. Something called high configurational entropy. As I mentioned, if you are aging more and more element, the configuration entropy increases. There is since you are having an element of different atomic size, you can see here there is called a lattice distortion. Lattice distortion in the sense, now you are adding a 5 element and each element have a different atomic size. You can see the size of A compared to size of E, or you can compare to size of B. Whenever you have a lattice, let's say this is a cubic structure. If it is ideal, everything is same size, you will see very ideal cubic structure. But the moment you are changing the size in each corner, you will see there is a distortion on the crystal lattice. Okay. The next one is called a sluggish diffusion. This particular group of this is little controversial. People have a lot of different opinion when it comes to diffusion. However, it shows a sluggish diffusion. Typically, this material, the reason of people behaving as sluggish diffusion is whenever you heat a material at high temperature, normally you see a huge grain growth. Right? All normal steels are alloy, titanium alloy, doesn't matter. If you at high temperature, you will see huge grain growth. But in high entropy alloy, you will not see a grain growth, or you will see extremely slow grain growth. And that leads to people believe that their diffusion is very sluggish, means slow. Where diffusions are high, you may expect to have a high grain growth. So that is the reason people believe that this has a very sluggish, which is good. Because when your grain is growing, you are losing the property. You know, there is a Hall-Page relation. Because of Hall-Page relation, you lose the property. When grain is growing, hardness and strength drop drastically. But if you are able to control the grain growth or restrict the grain growth, that means you can retain the strength and hardness significantly. And that is the beauty of this high. There is something called cocktail effect. This cocktail is a combination of various metals, A, B, C, D, which metal you want. Probably the combination of different properties coming from different material can add up or exhibit a multiple properties in one single alloy. So this is called a cocktail effect. There are a lot of thermodynamic aspects. I am not going on that. Just leave it. When it comes to fabrication, it can fabricate through the conventional route. Conventional route is basically melting casting route. You are well familiar with, right? Everybody is familiar with what is melting route, what is casting route. You can have a powder metallurgy route where metals are converted in the fine powder. You prepare alloy powder followed by sintering. So it has a powder, compaction, and followed by sintering, and this gives you the properties. Okay, so we have variety of sintering method. Similarly, we have variety of melting and casting methods. This can also be used through the deposition method, which we had discussed earlier, but there may be other deposition techniques. Material can also be synthesized, basically thin layers and coatings. By using the alloy combinations, you can have a coated layer to be in the form of alloy. So all three routes, melting, casting route, powder metallurgy route, and all coating or deposition routes are possible to synthesize this material or produce this particular group of alloys. Typical powder metallurgy route consists. Now I will talk a little bit more on PM route, as I have discussed earlier. Powder metallurgy group, those who are not familiar, I just trying to brief you. Powder metallurgy step consists of three stages. Okay, those who are familiar kindly excuse me, but if there is a possibility people may refine from different discipline. And here with what we have is first step comes is the making of the powder. Then next stage comes the compaction and shaping. There is something called compaction, or it is also referred as a shaping of preform of component. Third one is called a step called sintering, where material actually get a strength. Okay, so powder metallurgy has a 4 three different stages: powder making, then we have compaction and shaping, and third stage is sintering. In the present case, powder can be, again there when we talk about powder, powder can be prepared through various techniques. Atomization techniques you may be familiar, and then there is another technique called mechanical allying process. For high entropy alloy, what we do mostly, and most of the reported powders are prepared through the process called mechanical allying. Okay, you can see here the process called mechanical. So what you do in mechanical allying, you have all elemental powders A, B, C, D. You take it. Okay, how many powder you want to take in appropriate composition? You want equiatomic or you want different composition? You play with the composition, which fraction, which powder, which element you want, how much fraction. You take the raw powder, put in the container of a ball mill, which is, you can see here the signing ball, basically the ball which used for milling. Fill it, close it, and load in the ball mill. This is a high energy plenty ball mill in our lab, Prince P5. And of course, this comes in different shape and different size. You can have large ball mill, you can have small ball mill. Since we are in the laboratory, we have a small ball mill. But if you are a commercial production, you can actually have a large size ball mills. But their principle remain the same. So what we have here is the balls, which typically made of tungsten carbide. The container inside is also made of tungsten carbide. Balls are also made of tungsten carbide. These are the hardest ball and wires available, so that it can crush better. You have balls of steels also, but steel are softer, so it leads to a deterioration of the material, ball as well as container. So we typically prefer to use tungsten carbide, which is much harder and much stable. Okay, so this can be allied after few hours, 10 hours, 20 hours, 15 hours. You will see that this independent element, what you have seen, converts to a particular alloy. So this is the step of mechanical allying. Powder is produced. Then you can go for a sintering. Sintering can be done something called pressureless sintering. You make a compact and sinter in a vacuum or inert gas. You can also use a sintering through the hot press technique. So we employ both the techniques. Hot press, where powder is sintered while applying a pressure at high temperature, where in a pressureless sintering we do not apply a pressure during heating. So there is a two different sintering route called hot press sintering, and another one is called a pressure. So we involved both kind of process here. Both has their own advantages and disadvantages depending on what kind of component you are producing. Process can be taken. Okay, so this is brief about production of the high entropy alloy powder, which our lab basically involved in a mechanical allying route for making the alloy powder. We work in variety of high entropy alloy, not only one compositions. There are different aspects of work when we talk about high entropy. One is understanding the diffusion and densification mechanism. So, understanding diffusion mechanism is a very big thing, because we have a large number of elements. We need to understand how the diffusion of atoms are taking place. Then how to achieve a high density. For making a component, you need to achieve a high density. There are ways, different ways we try to evolve. Not all powder are good in sintering. Let me be honest. You need to really optimize the process. You find a ways how you can enhance the densification. Enhanced densification means how you can reduce the porosity or defect inside of the component, so that mechanical properties can be better and better. So that is one aspect, purely aspect on how to enhance the densification, which can be done through solid state sintering as well as liquid state sintering. So we also employ both the techniques called solid state as well as a liquid phase sintering to get a much denser microstructure. Third aspect is what we are dealing here is the making a composite of high entropy alloy. Using a composite, using high entropy alloy is one of the phase in the form of matrix. In another case, we are also using as a reinforcement. So we are also working, these are three major aspects which we are working on: development of alloy and understanding the diffusion behavior, achieving their high density, and of course, talking about their properties, evolution, all sorts of mechanical properties. And third one is try to develop some composite based on high entropy alloys. I just tell you some example how you can achieve high density through the pressureless sintering in this particular composition of high entropy line, which is 5-element equiatomic, where we have aluminum, cobalt, chromium, iron, and nickel. These are the constituent element of that Li, which is 5-element in equal atomic compositions. This Li is prepared through the mechanical ion route, and this after the Li is prepared, we study their chemical behavior and phase evolution. So to understand that, there is a technique called, you may be aware, something called DSC, differential scaling calorimetry. This tells you if phases, any kind of phases are happening, which lead to a exchange of heat. Exchange of heat. Any chemical reaction or phase reaction involves, phase transformation involves exchange of heat, either heat release, we call it exothermic reaction, or heat absorbed, we call it endothermic reaction. So at whichever temperature this heat really exchange is happening, either absorption or release can be accurately detected using the instrument called DSC, right? So this we can see here, the DSC profile is a function of temperature of mechanically milled powder. Li has been prepared. When you start heaping, you can see various things are happening. So this is a heat flow. This side is exothermic reaction. Other side is endothermic reaction. So you can see there various things are happening. Lot of things are happening. Is all need to be decoded, and you find several information. One most important information what I want to bring here notice is, you see small endothermic peak here, and there is a big endothermic peak here. This big endothermic refers to the melting of Li. Okay. Similarly, here also you will find certain endothermic peak. That means some fraction of Li is actually melting. So all the melting peaks comes in the form of endothermic peaks. If you look at the X-ray, these are the in situ X-ray where we actually heat and do the X-ray at high temperature. So we have in situ X-ray diffraction machine where you can simultaneously heat and do it. So I do not want to go details about phase. What I want to say here is, whatever Li you make, you can understand their phase evolution with the help of DSC. It will tell at what temperature, what kind of reaction is happening. And this can be easily be traced by looking at the microstructure and also in the, this is the X-ray diffraction. It started from room temperature and all the way it goes to 200, 500. We have taken some values, and you can see there with changing that their diffraction profile and phases, when you're moving from bottom to top, you will see that there is huge change in diffraction profiles happening, gradual change. And whenever gradual change in diffraction profile is happening, it does indicate that there is a slight change in the phases composition. So this is what I want to bring. I am not going detail of each peak. What I want to bring to the notice is that with changing temperature, the phases are changing, new phases are forming, some phases are going, some phases are vanishing, some new precipitates are forming. This you can all characterize using the X-ray diffraction, and which the signal, corresponding signal at various temperature, you can see using the DSC. There is another technique called dilatometer, which essentially tell you keep heating the samples, you will see a huge sinkage here. So this is the sample. You do the compact. So what is dilatometry means? Your dilatometry will be knowing that it is used for thermal expansion measurement. So you have a powder which you make in a compact, or we call it a pellet. And this pellet is basically when you heat it, material goes expansion and sinkage. It goes, if material has to be sintered, that means you are going to be a shrinkage, right? You are going to see the shrinkage. Sintering lead to the shrinkage. And you will see that when material green compact is heated, you will see this is the temperature which is accurately tells a 1047 degree or 1045 degree centigrade, the shrinkage. This is the length change. You can see the y-axis is a length change, downside is a shrinkage, where upside is a expansion. You can see this. This is the region where you see the huge shrinkage is happening. That means major sintering of the material is happening in this particular temperature range. I'll show a little bit more details. If you overlap DSC and dilatometer, this is a DSC profile, where this is a dilatometer. You can see that, notice, you can see the event which you have a melting, small melting, large melting. You can see that when the melting starts, actually the shrinkage starts. So this tells us that This particular Li is a liquid phase sintering going under a liquid phase. The moment liquid is formed, the densification repeats out. So this proves that this particular Li actually goes a liquid phase sintering. And if you look at the microstructure, what you do here, as we are interested more on microstructure, as I mentioned earlier, you quench them, you heat the material here and quench. We heat the material here and quench. So whenever you quench at different temperature, this is, let's say, somewhere 800 degrees centigrade, you can see the grains are unsintered. Very clearly grains are there. But if you heat it here at high temperature, somewhere 1200 degrees centigrade, you will see that these are grains, and what white phases, what you see is basically indication of wetting of the surface by the liquid phase. It's just something you have dipped in the liquid. And after the dipping, you will see that liquids are there. You can see very clearly the liquid are quenched. When you quench it, is frozen as it is, and you can see it around the grains, their liquid droplets has frozen out here in the surface. So you have a grains are weighted by the whatever small portion of liquid is formed. You are actually able to capture the liquid phase here. So it says that there is a liquid started forming at that particular temperature, and when you allow proper time, this leads to a massive densification. These are the temperature, different temperature. You have quenched the material at 800 degrees Celsius. You can see pure no sintering at all. You see 1000 degree, there is a little bit of sintering, grain coursing, everything. But it's a 1200 degrees centigrade. You will see that some of the fraction where liquid started forming. This is quench sample, just when liquid started forming. The white spot, what you see is the region where liquid start. You can see that hazy structure when liquid phase appears. And at high temperature and high room, you can see very clear that 1250 degrees, good amount of liquid is formed and weighted all the grain. So you can actually capture this event by using what is happening in the shrinkage side by dilatometer, what is happening in the thermal profile in the DSC, and what exactly looks like you can see in the ACM. Okay, so ACM, DSC, dilatometer, XRD, and ACM can actually tells the complete history of a changes happening in your LI. Okay, so this I have already explained. To understand, we go further, which is not much interest to you, is something called kinetics of shrinkage. So kinetics of shrinkage, there are a lot of modeling we do. What are the, basically when we talk about sintering kinetics, we try to identify which particular diffusion mechanism or sintering mechanism are acting for densification. There are a variety of sintering mechanisms, you all know. In this case, I have shown that this particular LI has a liquid phase forming. So what you do is liquid phase forming means the viscosity of a liquid which has formed plays a huge role. To understand that, we have characterized the viscosity of various elements. So some of the data has been taken from literature. This is the coefficient of viscosity, activation energy for viscosity. Aluminum, if it is formed aluminum solid, this is their viscosity value. If it is cobalt liquid, just at the melting point of their metal, these are their viscosity level. This is their, but chromium, if you have pure element, or I'm talking these are all pure element, liquid phase. So it has a coefficient of viscosity which has activation energy somewhere here. These are three blue lines. What you see here are for the high entropy Li, when it forms near their melting point, and it has their viscosity in this range. Their activation energy of viscosity is this range. And in our Li, which is actually a red color, you can see that when you measure their coefficient of viscosity, it will exhibit the activation energy in the same range. It does say that whatever phases we are predicting here, the liquid phase which has formed has a coefficient of viscosity exhibit the activation energy of what is reported for this high entropy Li. So it just says that this is another way of confirming the liquid phase sintering in our lab, where viscosity of your Li and reported Li are nearly in the same range compared to their base element. Base element has much lower. So it does indicate that this Li is melting as a whole and forming a liquid which has a viscosity altogether completely different than compared to their base element. So this also gives a very important conclusion about the viscosity of the Li phase and viscosity of independent element. There are a few more things are there. We have some other LIs called This is another composition containing a silicon, for example. And what we are doing is silicon, this particular is extremely hard and very high strength. However, it doesn't have a ductility. The problem is, our goal was to basically, can you improve a ductility while we can exploit the strength of this material? So basically what we wanted here is that you have this particular Li and use as some soft phase to provide a ductility. So here we have used as a soft phase as a nickel, pure nickel, which is a soft phase and which is expected to provide a ductility where strength comes from the high entropy Li phase. So this is a basically two-phase mixture we are designing so that you can have both high strength as well as ductility. You will see that property are, so this is typical powder metallurgy route, nothing wrong in that. These are their typical profiles, so you need not to worry about. The most important part here I want to show is when you talk about density of the Li. So what we have here is, we have a pure high entropy Li, silicon high entropy Li. We have added 5% of nickel, and in one case we have added a 10% of nickel powder. And we compacted and sintered. So their sinter density is morely in the same range of 96 to 97%. That is fine. When you look at their hardness, since nickel is a softer phase, but you can see their hardness does not change drastically because the base Li is already a harder phase, and nickel being a softer phase we expected, but it did not change. The hardness is retained without really compromising it. The interesting thing comes in their strength. You can see that this particular high entropy Li, which is converted in the black line, this has a strength of 1.8 gigapascal strength. I'm talking about 1700 megapascal strength. You can imagine 1700 megapascal is very high strength. But if you add a nickel of 5%, we are able to jump the strength to almost close to 3. By having a 10% of nickel, we have crossed the strength to 3 gigapascal, 3000 megapascal strength. So you can imagine how you can tailor this material to design ultra high strength material. You can call 3 GPa strength is ultra high strength material. It's a very rare to get a material which can actually have that kind of strength. So what we are doing here is a simple. You have a Li made through the mechanical line, which is nanocrystalline structure. Okay. This nanocrystalline structure of this particular has a very high strength and very high hardness. And by adding a nickel, we are providing a softer matrix. So there is a combination of high strength phase and soft matrix, and that has led to a massive combination of designing up material with a ultra high strength. You can see there strength of 3 gigapascal. You will never find such a high strength of Li. It's very difficult to find. So you can actually, this what I am trying to say is such LIs has extremely huge application or scope where you can design a high strength material. These are a simple microstructure. If you gradually increase in the microstructure at high resolution, you can see a lot of fine structures are formed here. You can see a lot of, by adding the nickel, huge amount of fine structure are formed. But if you look under the microscope, you have huge laminar and needle and fibrous structure are formed. And this formation of this fibrous structure and fine needle, which are basically nano needle, you can call it, is essentially is like a nanorod. Like huge amount of nanorods are formed, and these nanorods are fibrous structure has led to a massive jump in the strength. Okay, so it's a very simple techniques, but very effective techniques to design a Li with very high strength. These are more details anyway. Chemical analysis. So what we want to say here is we have designed a Li with very high strength. There is another techniques we try to do the development of some composite using this particular Li as a reinforcement in a pure titanium. So we use through powder metallurgy techniques, of course it is. So you have a titanium powder, pure titanium powder. In that pure titanium, what we are using HEA as a reinforcement here. So what we are doing, we have chosen a high strength, high entropy Li, which you are adding it 2% and 5%. Okay, and this particular pure high entropy has a strength this much, sintered one, and of course their sintered density is more or less same. However, when it comes to their property, you can see here the interesting part comes in the property. By adding This is for the pure metal. This is the hardness. This is the hardness of pure titanium or whatever titanium you have used. And by using, you can see the hardness has jumped. Hardness has increased. If you look at the microstructure, this is the titanium microstructure. The moment you have high entropy alloy phase has formed nice precipitates, and these are very hard phases is formed. And these hard phases actually, what you can see are the very hard phases, and these hard phases lead to a jump in the hardness as well as strength of this particular composite. So you have a plain microstructure to microstructure which has lot of precipitate, and these precipitates are very harder precipitates having a high entropy phase on it, and you are able to increase the strength and hardness significantly. Okay, we go for detailed analysis, not to worry about. If you look to compressive strength, you can see there is a gradual change in it. So this black line is, so you can see here the strength. Okay, the compressive strength of pure titanium is somewhere here, close to 1200, but this can be jumped by using the high entropy phase to almost 1500 MPa. So there is a massive jump from 1200 to 1500 megapascal by using such a just a small quantity of 2 and 5% of high entropy alloy. So these alloys can also be used. If we are increasing this composition, probably property will jump further. We just wanted to see even a small fraction of such high entropy alloy can end up having a high strength material. This is a case study of titanium, for example. Okay. Apart from that, when it comes to high entropy, there are various category of high entropy material has come. High entropy has led to various other categories called high entropy nitrides. Then we have high entropy oxides. Similarly, there is called high entropy borides. So variety of high entropy ceramics basically has also come in the picture, and these are extremely hard and very, very hard and very high temperature material, and it tells us that probably this category of material, high entropy ceramics, high entropy can replace your conventional ceramics and oxides for many high-end or extreme environment materials requirement. So with that, I just want to tell you that high entropy alloy material is extremely useful material. It is coming out. Since I said it is hardly 20 years, huge scopes are there in all aspects of material development, melting route, casting route, powder metallurgy route, deposition route. When it comes to the properties, there are a lot of properties has to yet to be evaluated. Their fatigue behavior is not well understood. Their creep behavior is not well understood. Again, or whatever studies are available are very limited, and those who are interested can find huge scope in this material to work on. It's a lot of things still to dig up, and we are working on, as across the globe people are working, and I'm sure you will find a lot of interesting things are coming out in high entropy alloy. So this high entropy alloy has led to not only the alloy, but it also same concept has been used to develop the high entropy nitrides, high entropy carbides. There is something called refractory high entropy alloys. Then there is something called high entropy borides. So this all comes with very high temperature, stable material, and this brings the opportunity to develop huge amount of new class of material as well as new kind of application for many of purposes. With that, I like to thank you all, and if you have any questions related to the high entropy alloy and typically PM processing, I will be happy to clarify the doubts.
Ravi Shankar sir, you can ask the question, sir.
Yeah, directly.
Ravi Shankar sir. Ravi Shankar sir.
Yeah. Am I audible?
Voice is not clear, sir.
Yeah, see, I just want to know what will be the price of electrolyte.
Pardon? I am not able to understand. Yes.
Just I would like to know the price of this. You mentioned for the electrometer. So just I would like to know.
Are you talking about equipment price? R sample and I'm sorry. Wait a second. You have to type. Let me check. No, I can't see. You are talking about price of a dilatometer equipment or the price of a running cost. So price of equipment varies. Two aspects are there, sir. One is the temperature, which will decide the. There is a huge disturbance. I don't know from where it is coming.
Ravi Shankar sir, there was a disturbance in your voice. Ravi
Can you
Shankar
mute?
sir.
I understood the question. Can you mute? Yeah. Can you mute? I can answer. Can you mute? Okay, fine. Thank you. So there are dilatometer comes into various range. There are various configuration. It all depends on specification. It comes typically on two form. One is, and that form is basically comes from temperature range. There is a dilatometer which comes with low temperature range. You can go 1100. Another dilatometer comes with a high temperature range, medium high temperature, which can go around 1600, 1700. And there is third range of dilatometer comes with ultra high temperature range. So which you keep increasing the temperature, the cost goes up, and costs start all the way from somewhere from 30 lakhs to 50 lakhs, depending on the specification.
Thank you.
Sure. Yeah, please go ahead. Manila Ravi Kumar.
Ravi Shankar sir, still any questions?
No. Thank you.
Ravi Shankar sir, your voice is not clear. I think there was some disturbance from your end.
I am again.
No problem. You can type now. If you want, you can type, sir. You can type, no problem. I will try to see the message. You can type now. I can see here. You can type here. Anybody has any question, you can type. I have opened the chat box so I can see it. Either you can speak directly or you can type there.
Sir, good morning, sir. This is Pawan.
Yes, please. Yes, Pawan ji, boliye.
Sir, actually, I have a doubt. So, how we have calculated? I mean, say that FCC BCC structure in previous session, sir.
Okay.
In HRD graph, how you have determined it, sir?
So this is very standard process, sir. That one, this is a standard characterization where whenever you do the X-ray diffraction, you get different peaks, right? So the location of these peaks can be characterized for their crystal structure. There is a standard crystallography methods are there, which tells which peaks belongs to which plane and which number of set of those planes belong to which crystal structure. So this is a well-defined old method techniques available. We use that technique only. We need not to evolve any technique. However, to understand their precise lattice parameter also, you can exactly find out what is lattice parameter of those techniques, again using the same. So it is a standard practice. We have not invented it. It is already on the process. We are following the same standard techniques what is available.
Okay, sir. Okay, thank you. Thank you.
And moreover, you can also see in a TEM. There is a TEM when you go to transmission electron microscopy. When you do the diffraction pattern, each of these crystal structure will tell you different patterns. That pattern you can exactly see in a TEM. So it confirms further what you are claiming.
Okay, sir. Okay, thank you.
Sure.
One more madam might have raised the question. Padma. Any questions?
You can speak, please. Whoever has a question, you can straight away speak if you don't have any problem with mic. Okay, I think.
Okay, sir. Next we will move forward.
Sure. With this, I thank you. Now I like to invite Dr. Sahil. I am removing. Sahil, have you joined?
No, sir.
Yes, sir. Yes, sir.
Okay. So let me introduce. We have with me Dr. Sahil Rohila. Dr. Sahil Rohila is a MTech as well as PhD from IIT Hyderabad. He has worked with my group. He has recently completed last year his PhD. Now he is still working as a postdoc, and he has basically involved in development of variety of this high. Many of the results what I have shown is his PhD thesis, but he is also involved use expertise in a phase evolution. So whatever I have showed is mostly the experimental one. We are doing synthesizing, quenching, and doing the manual job, right? But these things are actually used for verification. So you can using the computational tool. You know that these days we have a variety of computational tools has come. So using the computational tool, you know that you can minimize the setup experiment, for example. If you look at the 4 element, 5 element, 6 element, the moment you are adding the number of element, the Li characteristics become very complex. And you can imagine how many number of Li's you can come out. You cannot do experiment of each have thousands of element mixing in various composition. This is enormously not becoming day by day impossible. However, by using some of the basic fundamentals, basic thermodynamics, and some other physical metallurgy and other rules, you can actually minimize those experimental techniques. And in a computer itself, by using certain programs like phase field modeling and thermocal, many other thermodynamics based modeling, you can actually see whether the Li is forming or not forming. You know that by mixing any element doesn't guarantee you forming a Li. They may not form Li at all, or they may form a compound which you don't want, may be highly brittle in the nature. So what happened? You need to understand which kind of particular phases are forming, which kind of phases are stable under what temperature. These are very important. Then only you select that particular composition and particular temperature to make that Li. Otherwise, you will end up having a disaster and keep doing the experiment trial and error. When materials are become very expensive, it is very difficult to do only on rely on trial and error method. So these days, people are extensively use the computational tools to design a Li. And when I say the design of Li, there are few things are important here. One, the composition of Li, 10%, 20%, 30%, what we vary. And you all know that any Li, characteristics will changes drastically depending on their composition. Then their property. For example, whether the phase is stable at that particular temperature or not, whether that phase goes under phase transformation further alpha to beta to gamma, all those things, at what temperature they are possibly melting. So these all characteristics of the Li can actually be simulated before we actually think of. You may, by simulation itself, you can reject several of them. You find that these are not having, it is low melting, not having stable phases, having a lot of mixture of phases are coming. You don't want that composition. You can eliminate those compositions straight away. So you bring down that your actual production of the Li into very narrow by using these computational tools. So what I am requesting Dr. Sahil to demonstrate, since we are talking about high entropy Li, where you can imagine that there are 5 to 6 elements are there. When you have 5 to 6 elements, the understanding their phase evolution become complex. Also, at what temperature range those phases are stable, under what temperature those phases goes phase transformation. So before making any component or any application, you really need to understand this whole picture. And this you can actually see to almost 80 to 90% accuracy in your thermodynamic modeling tools. So this straightway minimizes your Li design and number of steps you want for experimental studies. So he will use these techniques and also run what his talk will consist of few things. He will have introduction of high entropy I have already given. He will have more introduction about the thermocal modeling. What is the basics through which you actually this thermocal modeling is developed, and later on he will actually have some case study where he will run the program here itself. Since he will be sharing the screen, you can see how phases are. You may be aware of the phase diagram, right? I'm sure all of you are aware of the phase diagram. Let's say I have a 2 element A and B, then I will know in a phase diagram at what composition it is forming a liquid phase, what composition it is a fully liquid, hard composition it will have liquid solid phase, or what composition it has alpha phase, gamma phase, this phase diagram. Now question is, how do you know that phase diagram when your number of alignment are increasing? It is just not possible to have experimentally determined. So these tools, he will demonstrate how you can predict the phase diagram for such a complex system. This is what is his PhD thesis and expertise. And I am requesting him to have a classical example. And so online, how the various phase diagram essentially tell you two things. As a function of composition, as a function of temperature, which phase is stable, which region you will get a mixed phase, which phase you will get a liquid phase, which phase you will get a solid phase, alpha phase, beta phase, gamma phase, SCP, BCC. All those structure region can also be known. This is what the phase diagram is. So he will tell you, demonstrate some of these things using this the next 1 hour. Please pay attention, and also those who are having some question, feel free to interrupt him. Okay, Sahil, you can put your video on for a minute so that people can see you. Now you are a speaker of a Sahil, can you? Okay, so here this is Dr. Sahil Rohila, which I am talking about. He is still in IIT Hyderabad working with our group, and onwards I request Sahil to continue the session. I will be now the whole session next 1 hour will be taken care by him. Okay. So, Dr. Reddy, Damodar Reddy.
Thank you, sir.
So, Sahil will take care of next of the.
Okay. Okay, sir.
Okay, fine.
Thanks for your nice contribution to this course, sir.
But by the way, anybody, any participant who has any question, please feel free. My email ID can be shared by Dr. Reddy. You will always feel free to write me later on also after the workshop, any kind of help, any kind of characterization, or any kind of things you think we will try. We are not promising everything. We don't know everything. But we'll try our attempt to resolve your queries or anything is there. Please feel free to write me. I will be very happy to attempt your any of the questions later on also. After even workshop is over, anytime. Okay, please most welcome to IIT Hyderabad. In case somebody is in and around, please feel free. So I request Sahil to carry forward. Okay, so bye everyone.
Thank you.
Bye.
So a warm welcome to Sahil Garu. So you can further continue as the sir told you.
Thank you for invitation, and
Sahil, can you speak somewhat louder?
Hello, am I audible now?
Now it is audible, Sahil.
Okay. So I'm very thankful to all of you for inviting me, and I'm really thankful to Bharat sir for giving such introduction, and he gave me a little bigger introduction I didn't require. So today in the meeting we'll try to discuss regarding the thermocalc and CalFET techniques for the high entropy.
Sorry for disturbance. Can you speak louder so that we can able to hear?
Okay.
Yes, you need to keep the mic near to you.
Hello, am I audible now?
It's audible, sir.
Okay, great. So I'm sharing the screen now. So is the screen visible?
Yes, sir. Visible, sir.
Sure. Okay. Thank you. So I am Dr. Sahil Rohila. I have just recently completed my PhD under the supervision of Dr. Bharat Bhushan Panigrahi at IIT Hyderabad. So today I'll be showing the techniques of the CalFET techniques and thermocalc and high entropy alloys, which is recently, both are the new techniques. The CalFET technique is also new, and high entropy alloys, the techniques is also new. So it has a really great future. So if any student would like to pursue, so I request that they shall pay attention. And if anyone have any question, they can interrupt me anytime. And okay, let's start. So this is the very basic material tetrahedron that everyone is aware of, in which the 4 limbs are there. So first limb is the structure, the another limb is processing, third limb is performance, and fourth limb is properties. So now there is one more circle enclosing in this tetrahedron, which is composed of computation. Computation is actually required to reduce the effort, experimental efforts, so that we can get to know the things very easily, and it also saves the times, material, and efforts. And as one of you, I have heard the question that how do you get to know regarding the phases FCC or BCC? So yes, if we move through the experimental techniques, there are several experiments that we have to perform, such like XRD and this TEM and diffractions to understand that whether the phases are FCC and BCC. So, but now if by using the computational techniques, first we can decide which phase we want, and depending upon that phase, we can select the composition, and then we can go into fabrication of the alloy. That actually saves much efforts. Um, so, so history of the this uh, Calfett technique. It just recently started in 2008 by US National Academics. So they reported on the Integrated Computational Materials Engineering and announces the Materials Genome Initiative in 2011. After that, and these are the just definition of what exactly the ICME and MGI do. So I'll okay. So Calfett is a actually initiative of MGI and ICME only. Calfett is calculation of the phase diagram, and calculation of the phase diagram can be done through various ways through molecular dynamics, Monte Carlo methods, and these methodologies. And by use thermocalc is one of the software which actually provides easier help to follow. So now these are the things of the basic of the simulations. First, we do the first principle calculation. First principle calculation are the calculation based upon the mass, charge, or electron spin. We get to know the position of the electrons, how they are behaving, what kind of spins do they have, and how their bonding will be. These are the first principle calculations, which are the base of the all simulation and computational techniques. Then it comes to the higher scale, that is Calfett. In Calfett, we got to know how these different molecules are behaving with each other. If they are resting together, if we are forcing, for example, aluminium and scandium together, how they will behave, how they will form like BCC, FCC, or Lave phase. That is the Calfett, the higher version from first principle calculation in the length scale higher version. Then the next version is the if we move forward, that is the phase field methodologies. Then our area also bigger. uh, for a bigger size area, we get to understand that how the minimization of energy happens and how the entropy and enthalpy will behave, how the precipitations will occur. That we get to know from the phase field methodologies. And the next step is using the finite element methodology. Above phase field, this is finite element methods, where we can get to know about the failures, that how the materials is failing if we put some kind of pressure on it or giving different types of loading. So this is how the computation starts from the very low scale to the higher scale. First principle calculations, Calfett, phase field modeling, which consists of Monte Carlo or other methodologies, and then this ANSYS and Abaqus we use usually for finite elements methodologies. So these are the main things which thermocalc provide. Thermocalc actually works on the minimization of Gibbs free energy, which is a function of x is the molar fraction, T is the temperature, P is the pressure, and N is actually N is the number of elements. Also, it is also a function of that. So in which we can do two types of major calculations. One is thermochemical measurements, in which we can calculate the enthalpy of formation, entropy at any time, heat capacity such as that is specific heat capacity and heat capacity, Cp and Cv, heat cap and its activity. The another thing that we can perform is phase equilibria to get to know the liquidus temperature, solidus temperature, or phase equilibria, that number of phases are stable at particular time. So thermocalc actually have the thermodynamic database. The database is based upon the experiments that we have performed in the past. It consists all the results from those experiments, and then we use thermocalc. Thermocalc then extrapolates using that thermodynamic database. For example, there is some A is there, B is there, and D point is there. For just wait. For example, point A is there, B is there, and D is there, but this point C is unknown. So thermocalc has this database of point A, B, and D. So based on that, it will extrapolate and will get to know the point C. This is the very basic principle how thermocalc exactly work. For example, we have, sorry, I'll make it here. This is temperature. This is something quantity, unknown quantity F. We have, this is 0 Kelvin, I'll say. Most of our work above nearly 300 Kelvin, but we have information till this point, so it will help to extrapolate and get to know the results. And based on using this thermocalc, we can actually make this phase diagrams. So we'll see in next thermocalc. So there are different modules in thermocalc. One is we can do single point equilibrium. Through single point equilibrium, we can obtain the values of enthalpy, entropy, specific heat, or solidus temperature, liquidus temperature. The another technique is phase diagram, which can be binary. We can also make ternary phase diagrams. So is all I think all of you have idea about phase diagrams. If you do not have, you can please let me know. I can discuss within a few lines. Okay, I'll just say basic. For example, if our we have single component, we have one component, so we'll identify the stable phases with respect to temperature. If we have just one element, we'll just get to know as we heat temperature. In this direction, if we'll vary the temperature and the amount of phases, the phases stable are, we can get to know here. So if the number of element is 1, so the phase diagram will be a single line. If the number of element are 2, such in case of iron carbon diagram, I hope everyone is aware of the iron carbon diagram like this happens. So in or any two, I'll just say A or B. So for if the number of elements are 2, it will compute to the area. Okay. So if the number of elements will be 3, so the phase diagram will be actually a volume. Still, we can observe that volume in a 2D plane. But if the number of elements exceed beyond 3, how we can process those things? In that case, we actually make pseudo binary phase diagram. For example, we have phase such that A, B, C, D, and E. These are the elements that we have. So how we obtain the phase diagram now? Because it is very difficult. So what we will do, we'll fix the composition of 3 elements at a point and we'll make pseudo phase diagrams, pseudo binary phase diagram. That's A and B, while C, D, E are fixed or constant. Then A and C, A and D, similarly A, E. We'll actually make phase diagram of all the possible elements and then we'll confine the results and get the data. Just similarly B, C, B, D, B, E. Okay. So these are the phase diagrams that we can make through this thermocalc. The another is the Scheil solidification. So Scheil solidification is based upon the Scheil equation. So it uses the same approximations, assumptions while computing the solidification. The another module of the thermocalc is DICTRA. DICTRA is for the diffusion calculation. For example, I have iron carbon diagram, or you can take any, whichever you can think. For in case of iron carbon, so I want to see if the temperature is changing, or if the temperature is, we can take any case. For example, the first case is now temperature is stable. I want to give it a 300 hours time. How the carbon or the ferrite boundary will change with time. So that we can process through DICTRA. The another module is PRISMA. PRISMA is the precipitation calculator. For example, it is mostly used in nickel-based superalloys, and where we have to study about the gamma prime precipitations. The another is property calculation. Property calculation is we can actually obtain from all of this. So we'll see now. Just wait. So this is thermocalc. Is everybody able to see? Because I'm not getting any response, doubts or something like this. Am I clear to everyone?
Yes, sir.
Okay. So if anyone have any doubt or query, they can interrupt me in between also. So this is thermocalc 2019A. So it have 5 basic windows, 5 basic pane. One is the project pane, which will provide us the information that on which project part, which part of the project we are there. The another is the configuration window. Here you can see the things which I have explained earlier, the single point equilibrium property diagram, phase diagram, and all those things that we use for to progress in the project. The third pane is the event log. It will tell that whether the project that we have, whether the assigned job has been started or not. If any errors are there, it will let us know the errors. The another window is the result pane. It will give us the results. So this is the very basic. So I recommend that those who are very serious, they can grab a pen and paper so that they can get to know the how I am performing these calculations. So Thermocal provide two basic modules. One is the graphical module, that is the graphical user interface, GUI. The another is the console mode. In console mode, we have to just give the programming write code, just like Python, and we can import the code also in the MATLAB, so that we can use that code or the results obtained through Thermocal through our manual user defined functions. So I'll use the graphical user interface so that you can observe clearly. So let's start from the very basic, the single point equilibrium. Okay, so now you can see the configuration pane has been changed. A periodic table has been appeared here, and what type of calculation we can do here, we'll see. First, I'll do calculation for a 2D binary alloy, and later I'll expand it to entropy alloy. For example, I'll see there is a database for, just like I have explained it in the first slide, that we have to select the database first. It used the experimentally available database. So I'm using this iron carbon only right now. So I have already selected database iron and carbon. Here in this pane, I can give the based on the mass percent, mole percent, mass fraction, mole fraction. So I will prefer inputs from you actually. So if anybody can unmute the mic on through which we can do. So I can right now I'll go for mole percent. So please let me know how much carbon you want in the alloy.
5%.
Okay, let's go for the 5%. So on the next page, we'll go, and I have selected the temperature. Okay, what temperature shall I select? You want at what temperature you want exactly the equilibrium condition?
980 degrees centigrade.
Okay, 980 degrees centigrade, very good. Celsius. And now I'll just go with the perform tree. It will take a little time. So I'll most of the things I'll cover, which will take lesser time only. So it shows the activity table render executed in 121 microsecond. It has been executed. So here in the project pane, now you can see that system definer was the first place where we selected our element. Equilibrium calculator is the place where we give the conditions, that thermal condition or pressure condition like this, and table render is a place where we obtain the result. So we'll go to the result pane. I'll select the result, and we have obtained at temperature 1253 Kelvin. Okay, so it is giving in the Kelvin, but the component, the phases table are FCC. It is giving, if I'll select composition and constitution, it will exactly give how much carbon is there in by mole fraction and how much iron is there in the iron mole fraction. And we obtained these phases. Now we know the stable phases. For example, I have a very new composition. I do not know. If you want to add any other material and another element,
You add the phosphorus.
phosphorus. Okay, phosphorus. I'll make 0.2. Let's see. Then I'll go to equilibrium calculator. I can go by through project pane also, or using this arrow. And I'll select table render Celsius perform. Okay, so it will give now the total gives free energy, this enthalpy, volume, and now we have phosphorus, carbon, and iron. So let's go to the very real case where we usually use 2%, equilibrium calculator. I want to show you the stable phases. We'll go to 200 degrees centigrade. Perform. Why it is not showing this cementite and others? Okay. Now the thing which I want to show. It is showing now graphite. Are you able to see graphite? Hello.
Just
Let us
a
see.
minute.
Yes, sir.
So graphite. It is showing now graphite. But have you ever seen graphite in the iron carbon diagram?
Because it is cast iron, so here graphite may be there, no?
Yeah, but mostly graphite is unavailable. Very less amount of graphite, yes, sometimes present. But cementite is the thing, that ferrite. So cementite, actually,
Yes.
we need cementite, and we observe cementite a lot in the this iron carbon diagram and the steels.
Excuse me, sir, but the carbon, what percentage you have taken? It is representing the cast iron. It's a
Exactly.
5% carbon you have taken. So carbon contains the graphite.
Yes, sir. Right now the carbon percentage is 2. So let's even make it to 0.5. Will that be fine?
That will be fine.
Still we are observing graphite. So the main thing, actually, it is doing the global minimization. If I'll show you, yeah, here. So, so this is the metastable equilibrium. Cementite is usually at the metastable equilibrium, and graphite is the main equilibrium. So it is giving the global minimization. So in case I want to check, because there will be many types of alloys where the complete equilibrium will not reach. So in the steels, cementite will transform to graphite, but the activation energy is so high it will not reach to the graphite, but it is giving us a little different information. So how we can process this? We will go to equilibrium calculator, options, and we'll uncheck the global minimization. We'll go to table render, perform. It is giving now error. Select. There is some different information. And we'll go to system definer. In phases selection, we'll uncheck the phase graphite, and then we'll get to know cementite. Just wait. Now it is giving the cementite FCC diamond. Yes, okay. Some because maybe because of another composition, but it will give cementite once we uncheck the graphite phase. Now let's expand this to the high entropy alloys. For example, now I want to use any high entropy alloy. I do not know the composition. I just want to select any elements randomly. For example, I want to use cobalt, nickel, iron, chromium. This is the Cantor alloy, cobalt, chromium, iron, manganese, nickel, one of the first alloy. And I'll give mole percent to 20, 20, 20. So now I have given one element, which is my element. For example, I want to work for a very long period on this alloy only. And this is very easy giving composition here, but sometimes the alloy contain many number of elements and very weird composition, for example 0.003, 0.001, like this. So in such case, I can save my material as Cantor alloy, save, yes. So in future, I can directly load my material from the library, and I'll just get these things. I'll change the database to high entropy alloys, and then I'll move forward. Conditions, I'll select nearly 1000 degrees centigrade and table render. I'll get to know the results. Right, it is running right now. it is still running activity. Yeah. So it has run. It is giving me the stable phases of this particular high entropy alloy is FCC only, and constitution and composition will provide that in at that point it will be equal composition of all the elements. There will be no segregation of the phases. Now, if we cobalt, chromium, iron, manganese, nickel, that is the Cantor alloy, is FCC phased alloy. If I'll add aluminium to it, for example, and I'll uncheck the this manganese, aluminum 20. So now earlier the phase was FCC. Now we can see. Just wait. Right now, this is the thing I would like wanted to show, that when we had Cantor alloy, it just show FCC phase with an equiatomic composition. I just wanted you to know that please do not get. I thought that you may get confused with, because I have provided here equiatomic composition, and it was showing equiatomic composition in the result pan also. But look here, as I have changed from manganese to aluminium, it provided me that there are two types of different BCC phases are present at that point, that is 1000 degrees centigrade, among which one is a chromium rich region, it is showing, and another is nickel rich region, it is showing nickel and aluminium rich region, and that is the exactly what we are observing through experiments only also. So if we have any other different temperature, so here we can select the quenching temperature, or if we want our alloy to perform at such and such temperature, and before making that alloy we can get to know that yes, there is a sigma phase is also present. So if we change our temperature from 1000 degrees centigrade to, let's say, 1200 degrees centigrade, will sigma phase will be there or not? So now we get to know, no, only two different BCC phases are present. One is chromium rich, another is a nickel and aluminium rich phases are there. Both are BCC in nature, and we'll just get to know the through the XRD and TEM. Yes, they are only BCC phases. So what else we can do from this equilibrium calculator? We can calculate the solidus temperature also. So equilibrium, we can right click on the node. We'll create one new successor, equilibrium calculator second. We'll go to advanced mode. So after going to advanced mode, I can add one more activity here. I'll fix the phase. I'll fix the liquid phase. Yeah, I'll fix the liquid phase to 0. I want to find out the temperature, so I'll uncheck this. So please look at here also. If I'll check this box, it will say number of missing condition is -1. If I'll uncheck this, it will show number of missing condition is 0. If I uncheck this also, it will say the number of missing conditions are 1. So it is just like quadratic equation. When if there are number of variables are 3, we need to define for 2 variables, 2 different boundary condition we have to provide to find out the value of third. So if there are 4, then we have to define the number of 3 variables, and we should provide 3 boundary conditions to obtain the value of the 4. Similarly, if we'll provide the value of all of these, it will provide mean the number of missing conditions as -2. It will make the intermediate solution, and it will not resolve. So I want to find out the temperature at what and at solidus point. Solidus point, the liquid content will be 0. I'll right click on it, create new successor, table render. I'll check the temperature, Celsius, perform, and it will give me at temperature 1346.97 degrees centigrade is the solidus temperature of the high entropy alloy, and at that point liquid fraction is 0 and BCC fraction is 100%. Okay, So now we'll go back to this. It gave the answer 1346.9. We'll put 1350 degrees centigrade here. And check the phase. We'll check the phases. The number of phases contains now liquid 0.09 mole fraction. So are you able to understand what was my point? That how to calculate the solidus? We calculated the solidus point from another calculation, and we rechecked it from the first calculation. So this is the single point equilibrium, that we provide all the conditions, and we want to check the condition at a particular point. Is it clear till now, or you have any doubt in performing, and or you want to try by yourself, that you'll dictate to me and I'll perform? You want to, one of you would like to do like that?
Participants. Participants.
Hello?
Hello,
First thing I would like,
anyone?
okay, to all the participants, I would like to ask two questions, basic. First thing, am I audible to you?
Yes, sir. Audible, sir.
And the second question to the participant, that whether you able to understand this or not. If not, please ask me doubt. Please ask me how to perform these things, because in future this will be really helpful to you. One thing, that this is a lecture, not presentation, so I do not go through and cover all the topics. I want to cover those things which you can understand easily, which all of you can understand easily, and use that thing in your future.
Participants. Anyone? Are everyone kept muted and left the computers? Sir, with great pain and time he is spending to us.
Okay, if anybody
Okay,
would.
sir, you can go further.
Okay. So this is the single point equilibrium, which is the first portion of the thermocalc, that at particular point we provide the exact condition that we need the number of phases. What will be the number of phases at that particular point? It will provide the value to us. We want to calculate the value of enthalpy. Yes, we did not calculate as of now. Yes. So I want the value of enthalpy or entropy. Enthalpy. Now per mole, I want enthalpy of particular phase only. I want enthalpy of liquid phase. I'll add this. I'll perform. Here in the, I'll get enthalpy of liquid. Now what we can do with the enthalpy of liquid? Now we know how much amount of energy I have to provide to convert from solid to liquid. The energy required from solidus to liquidus. And with the help of that, I can also calculate the specific heat. Because enthalpy is none other than Cp delta T, m Cp delta T. M is the number of moles, number of mass is, I kept in moles are 1. I can also change to mass in gram. For example, it will provide me the value of enthalpy for 1 gram. So now this is the value of enthalpy, 907.5 per gram, joule per gram. So mCp delta T, I know the delta T. The solidus temperature I know, the current temperature 1350. I have the delta T. I have the mass, that is 1g. So if I'll divide, I'll get the value of specific heat at constant pressure. Similarly, I need the internal energy. I'll add one more column here. I'll select this internal energy. I'll perform, and I'll get the data of the internal energy. And from internal energy, I can also know the specific heat at constant volume. So these are the things that we can calculate through single point equilibrium calculator. So now I will move forward to the binary phases and ternary phases, how to develop phases by using the thermocalc. Will that be fine if I'll move forward? Okay. So I'll calculate the phase diagrams now.
Yes, sir.
Before going forward, I'll actually delete all these past activities, so that will not get confused. Remove. Okay. So first thing, the selection of the database. So I'll select, for example, now I want to check the phase diagrams of aluminum. I'll select the aluminum database. Okay. Aluminum, I want to check its phase diagram with scandium. I don't know how it will behave. I'm giving randomly that at scandium 10 mass percent or mole percent, how the things will change. So I'll go to the equilibrium calculator, and in phase and phase constitution, I'm giving freedom to all the phases, that all the phases can get stable. I'm not providing any limitation that whether this phase should be there or not. I just want to check randomly because I do not have I have zero idea about the aluminum and scandium, that how the things will be. So I'm giving freedom to all the phases. I'll go to equilibrium calculator. I'm providing Celsius, that we need temperature in Celsius. Then mole percentage of, then we have to provide the quantity, that mole percent of scandium from 0 to 100. And temperature, we want 0 degree centigrade to 1200 degree centigrade. Next thing is plot render. In plot render, I want with the composition of scandium or aluminum. I can go through both, either of them. I'll uncheck this automatic scaling of 0 degree centigrade, 1200 degree centigrade with a step of 50 degrees. Check perform. It will start computing. Okay. We have obtained the phase diagrams of aluminum and scandium here, if you can see. And as I hover at any temperature, I want at 550 degrees centigrade. It is providing me that at 550 degrees centigrade, FCC phase is there with the precipitate aluminum 3 scandium. I want to increase the mole percent of scandium, and it is giving me this AlSC2 plus AlSC. Now it is a binary phases, and even if I'll go and right click over it, add label, show details. Now at this point, I can observe, and I'll select here composition and constitution, same here. So my system is at 14.28 mole percent of scandium at 950 degrees centigrade. What other phases will be there? One is Al3SC with a molar fraction of 0.47. The another phase that I have is liquid at 0.52. So it will tell me that at which point how much phase of how much phase and which phases are present. If I'll say okay, it will just write it here. If these things are clear, that how to use these basic things. And in plot render, this is a legend style. Legend style is none. If I'll provide all, it will give me all the proper information of the phases here. Now you can see. It will give me FCC phase is there, aluminum based plus Al3SC. What if HCP phase is also possible, plus with BCC disordered phase, and these blue, violet, yellow color line are showing that particular phase. For example, this thing I'll do, double click on this, right click, properties, I'll increase this width. Now we can see HCP is this color, so which is this. So here we are obtaining HCP at, double click the point, sorry, right click, add label, show details. At 90 mole percent of scandium, we are observing HCP phase. So this is the binary phase. Now how to calculate the phase diagrams of high entropy alloy? So we'll go back to system definer. So the first thing was selecting the database. So we'll select the database of high entropy alloy. We'll select any alloy, for example, cobalt, chromium, iron, manganese, nickel. So high entropy alloys are the simple solid solution of 5 or more elements in equiatomic or nearly equiatomic proportions. So I'll provide. How many are there? 1, 2, 3, 4, 5, 6. I'll reduce to, I'll use 20, 20 each. So if the number of elements is 1, the phase diagram will be a single line. If the number of elements are 2, it will be a area. If the number of elements are 3, it can be a volume, or we can reduce it to ternary diagram. And as it contains higher number of elements, so we'll fix one variable. As you can see, the composition of cobalt, we cannot change it. That is a dependent. And the independent variable we will select in the phase diagram while plotting the phase diagram. So in equilibrium calculator 3 will go here, where I can select the which is the independent element. It can be iron, manganese, chromium, or nickel, but it cannot be cobalt, because cobalt I have given here as a dependent variable. There are two things, which is dependent variable and independent variable. I can change this dependent variable to iron or any other. Okay, let's plot the phase diagram where iron is a dependent variable. As the composition of, okay, I'll first plot the phase diagram, then I'll explain it to you. So I want mole percent of nickel, dot render nickel, legend all. Okay, perform. Results. It will take some time. So meanwhile, I explain what are the dependent variable in phase diagram and independent variable. For example, I have four elements, A, B, C, and D. So while plotting the phase diagram, I'm keeping the B and C fixed, that this composition of these two elements will not change. And the composition of A element is dependent upon the composition of D element. As the composition of element D will change, it will automatically change to keep the total composition or stoichiometry equal. Just in iron carbon diagram, you can see as we change the composition of carbon, in that carbon is independent variable and iron is dependent. If composition of carbon will go from 2 to 5, the composition of this iron will decrease from 98 to 95. Is it fine? Are you all right about dependent and independent variable? How I have selected, and what is the main basis of that? Okay, we'll see phase diagram as soon it will get computed. And could you please let me know how much time do I have to discuss more? Because I can go on, and that is fine. But till what time I have to discuss?
Sir, you are having time up to 12:45, sir.
12:45. Okay, so we have very less time. So okay.
Still, your requirements actual time up, we need to complete by 1:15. But the session was started early, so I told you that 12:45.
Okay. So phase diagram is one of the important things in high entropy alloy. That's why I just directly jumped on the phase diagram. Even in between that, there is a property diagram is there. Okay, we'll see the phase diagram first, and hopefully I'll discuss more about phase diagram, and then we can complete the session. And if anyone have any doubt, they can contact me anytime via email. So I'll be happy to help to all of you. And meanwhile, the phase diagram is getting computed. They can ask their queries, questions, or something like that if they have anything in their mind. So even if it is not related to thermocalc, even if it is related to high entropy alloys, powder metallurgy processing, or any such a question, if they have, they can ask. I'll be happy to help if I can help. I'll try to help.
May I know the name of the software and how it is will be available to us?
Okay, so the name of the software is ThermoCalc. That is based on from the thermal calculations. So you can
Okay.
download it from its website. And this is ThermoCalc, and in they provide few databases for free. That is demo database, and by using those database, you can also calculate so many things. You can do diffusion calculation. You can calculate the precipitation. For example, in aluminum alloys, we can get this precipitation that how
Okay, sir.
G, G, G.
Okay, I understood. Now you go ahead.
Yeah.
Thank you.
So calculation of phase diagram is actually lengthy process because it have to compute so many database and data points. I really wanted to show you a phase diagram, but it is taking time. Okay, I'll show you from one of my own. Just wait. So this is the type of phase diagram for high entropy alloys we get. This is for one condition. So to for high entropy alloy, we actually have to process so many phase diagram. I should just wait. So this is for aluminum, cobalt, chromium, iron, nickel. So for this, we actually have to develop nearly 22 phase diagrams to get to know the how the phase will evolve with time. So here we can get to know about the mole fraction of iron, and here is aluminium and iron. Aluminium is a dependent variable, iron is independent variable, and cobalt, chromium, the composition of cobalt, chromium, and nickel are fixed, and we get to know the how the phase will evolve with time. So similarly, the next phase diagram will be when cobalt is a dependent variable and iron is independent variable. So the phase diagram will be a little different. So we have to compile all the phase diagram, and then we have to understand that how the phases are changing. So this is how we exactly get the phase diagram for high entropy alloys. Now the sub process completed normally. This is really good. Right? So for this particular alloy, between 0 degree centigrade to 1200 degree centigrade, this is the phase diagram that we have obtained. And if we want to check that this region, just hover it and it will provide the value of the phase, that FCC plus sigma. If I right click, add label, okay, so the label will be added. I can save this phase diagram, which is one of the most important part of thermodynamic calculation. Just save as a PNG, JPG, or TIFF format or PDF format. I can directly save the phase diagram and use it later. So if anyone have any question, they can let me know, because if I'll move into another domain, that is diffusion and precipitation, it will take another 15 to 20 minutes. And the phase diagrams, this binary and ternary calculation can be done through phase diagram only. I can show you here. So attain level, vertex scaling. Yeah, show triangular. Triangular. In triangular, if I'll put it triangular, I'll get the ternary phase diagram type. Perform. And here are the. So these are the binary and ternary calculation which I have covered. So what all the things I have covered? I have covered the single point equilibrium. From single point equilibrium, we can calculate the exact functions such as enthalpy, entropy, solidus temperature, liquidus temperature, or specific heat. These are the things that we can calculate from the single point equilibrium. Property diagram is the amount of phase. I can show you. In the phase diagram, the main thing is how the phase will behave. The phase will change with respect to temperature if I'll fix the composition. Binary and ternary calculations are the part of phase diagrams only. I have shown you the end results. So one more thing I can show you is the property diagram. Property diagrams are the in calculation are the 1D program. It is a one-dimensional program that the number of phases will change with respect to temperature. In phase diagram, it will show the how the phase will change with respect to composition of any element and temperature. But property diagram are the how the phases will change with exact composition with respect to temperature. For example, I'll for fast calculation, I'll select iron and carbon. I'll put 5%. Steel database, equilibrium calculator 3. With respect to nickel, no, okay. Database is steel. Actually, property, yeah. This is the steel equilibrium calculator. Want temperature from 0 to 1500 degrees centigrade. Property diagram, float render, automatic scaling of 0, 1500 degrees centigrade. Amount of phase per mole. Or I can, for example, I need just cementite phase. How the cementite phase will behave. Perform. We'll get the result within a minute because these are the binary calculations. So it is not providing any cementite. Yeah, if we can see here, no, it is not cementite because I have to, because cementite in global, actually graphite have a lower Gibbs free energy than cementite. So if we want cementite, we always have to uncheck graphite. Perform. Still we are not getting. Okay. All phases perform. Here are the all possible phases are there, and cementite is in this region. Properties. Okay. This is the cementite line. Suddenly at this point, and these are the iron and carbon diagram in which the composition of carbon and iron are fixed, but it will just tell us the mole fraction of the phases, that this phase is BCC, which will have 80%, and the another phase is diamond FCC, which will be nearly 20% till 0 degree centigrade to 860 degrees centigrade. At 860 degrees centigrade, cementite will form, which composed of nearly 78 degrees percent, and the another phase will be the BCC, will be of 20%. And this is how we can obtain the data of phases of a particular composition and fixed composition with respect to temperature. So the module that we have covered today are single point equilibrium, property diagram, phase diagram, binary and ternary calculations. So the other modules are solidification. We get the solidification curve, diffusion simulation, and precipitation simulation. Shell solidification I can also show you within a minute. Shell solidification actually use the same assumptions that of Shell equation and the solidification equation used for the solute redistribution. So the assumption it makes are the diffusion should not be there in the solid state, solid phase, and very infinitely fast diffusion will be there in the liquid phase. So we can use for the entropy alloys. For example, I have a entropy alloy cobalt iron, this time titanium, manganese, nickel. I want 20, 20, 20, 20. Yeah. And the next part, I'll just check if the nickel is the fast diffuser. I'll check the nickel is fast diffuser. I'll select the starting temperature to be 1800 degrees centigrade. I'll select the Celsius and temperature. Yeah, I'll keep this normal and perform. Within 5 minutes, I'll obtain the solidification curve. For example, I have an alloy. I want to see for the it is very helpful for the melting casting route that alloy is solidifying. I want to check which phase is evolution precipitating at the first. For example, there are laminar flow, so many things. Actually, many things are there to control, but we'll get to know. Degrees of freedom 0. Just 2 more minutes, I think. We'll able to get the results. So earlier, actually, as we obtained this property diagram, it is telling us here that the liquid is green line. That above liquid, above this temperature, above 1423 degrees centigrade, our phase will completely transform into liquid phase. So shell solidification is a reverse of property diagram. It will start from liquid. Then the first phase will which will crystallize is cementite and FCC. So the if I'll reverse this property diagram, I'll get the shell solidification. Here you can see. First thing, please check. The dotted line is the equilibrium line. And I'll properties. Here you can see now. The dotted line is equilibrium line. The blue line is liquid and liquid plus BCC. So here we can see as it is coming down till 1120 degrees centigrade, BCC phase start forming in the alloy. Apart from the second and another BCC phase plus lave phase start forming into the alloy as at nearly 1100 degrees centigrade. So we get to know how the phase or how the alloy will get solidified through melting casting, or if I want to do any quenching, then in that case the property diagram is very helpful. For selection of composition or stoichiometry, property diagram and phase diagrams are helpful. So I'll stop it here. So if anyone have any question or doubt or suggestion, please let me know. I'll be happy to take. I hope this talk will be useful to you, because I wanted to cover so much area, but at every section I wanted to show you the high entropy, that how we can use thermocalc for high entropy alloys, because binary and ternary calculations are easy, but high entropy calculations are a little difficult and different from the binary and ternary calculations. So I wanted to show you all those things. So if anyone have any questions, please let me know. Hello.
Sir, is there, sir? We are there.
Okay. So, sir, so can I stop here, or if anyone wants like to know anything more, I can tell.
Dear participants, are you interested further, or you can ask any questions to the sir, so he can helpful to you. Hello, participants. Participants, I think it's time to wind up, sir. So they are
Okay. Yeah, because they are
afternoon, right?
since morning.
It's almost 12:50.
Okay.
So I think
So,
they may be feeling hungry, and they left the session by keeping the mobiles on.
Yes, sir. So I'm writing my email ID here.
Okay, sir.
So anyone can contact me through this email ID or through LinkedIn if anyone have any question.
One minute, sir. I will note down. Yes. J- Shahil Rohila 1@gmail.com.
Yes, sir. So
Please, if anyone interested to ask the questions, please ask the questions.
so okay, so in future, if anybody would like to contact me, they can contact me through email ID I have written down in this message box. So,
Okay.
so shall we wind up, sir?
Yes, sir. Please continue.
Okay, so I'm really thankful that you gave me opportunity to explain about these techniques, and I'm really happy to do all these things because I need and I want actually people to get interested in this simulation area because this will be helpful in their future because experimental techniques and experimental methodologies are coming to actually cease down because they take a lot of efforts, a lot of trials, a lot of experiments, and money also is there, time factor is also there. So look, within within 30 minutes we able to compute so many things. We able to get to know how this high entropy alloy will behave at such and such condition, what will be the specific condition. But in earlier case we have to run complete experiments for complete even for a month, and if any impurity will come in the high entropy in the alloy, then the all experiment is gone. But now within 30 minutes we are able to complete that many experiments which may took 1 year within 30 minutes. So this is really good software, so all of you can learn. And yes. Thank
Someone
you
has
very.
asked what is the name of the software, sir?
So software name is thermocalc. Well,
So you please type it. That will be
yes sir,
useful to them.
thermocalc. And student version, yes, student version have many databases, demo databases, aluminum based, iron based, nickel based, and SGTE database, which you can use for the basic calculations. Yes, they contain some databases which will be helpful.
So sir told us the name of the software is ThermoCalc,
Calc.
which will be very much useful for simulation purpose. Without simulation purpose, I feel that it will be very difficult to conduct an experiment real time. So that's the advantages of this simulation packages, that which saves a lot of time and money, and wastage also can be reduced. So that once we got this is the result that we are going to get, then definitely we can proceed further, and then we can optimize further if there is any changes in design like that. So I need to thank Sahil Rohila for giving the valuable presentation that will be useful to the participants in further research work. The people who are interested in the research work, that will be useful to them, because frankly speaking, the adults that I faced during my completion of PhD, I used to send the sample pieces to sir, and sir used to conduct the experiments like you, like
I think some issue is there. Hello. Actually, I'm unable to get the sound. Yeah. Maybe sir has some issues with the internet, I guess.
No, sir, some network issue, I think so, sir.
Yeah, yeah, I guess. So can we end here, or we want to proceed further? What is the present status?
Sir, just be in line, sir. I will intimate you, sir.
Sure.
Power cut
No.
over here, so I can't able to complete the session. Sahil sir, thanks for your valuable lecture, and this particularly this session will be useful for those participants who want to complete or do the research work in simulation area. So again, we will meet at exactly 2:15, and the next session will be taken by Mr. Dr. Ravi Shankar sir from IIT Tirupati. Okay. Thank you, Sohil sir,
Okay.
for your
you.
contribution. Thanks one
Okay.
and all.
Okay. Thank you very much, sir. Thank you, Rajesh
Thanks.
sir, and thank
Thank
you
you.
to
Thank you, sir.
thank you, Damodar sir. Okay.
Thanks, sir.
Thank you.
ఈ యూనిట్ ఆగిపోయింది